Okay, so we have the differential and linear approximation. So I'm going to write down a definition for you here. But this won't make sense to you until I draw a picture, I don't think. So I'm going to go ahead and try and draw a picture. But if you want to write down the definition, that's not bad. So how do you even read what's on the screen? What's that first line say?
Thank you.
Bless you. dx equals,
Change in x.
okay, delta x, or the change in x. All right? And maybe the other thing I should tell you guys is, notice what I didn't write. I didn't write dy equals delta y. That's not true. Okay? dx is going to equal delta x, but dy does not equal delta y. Okay? What does dy equal, it says? F prime of x dx. What does f prime of x mean? Yeah, what's f prime of x mean? Derivative, okay? So you need to learn the derivative before you study what a differential is. We've done that. And then what I mean by the differentials, I mean the little dx and the little dy. Those are little symbols. And now I'm going to show you what they mean using a picture. Okay? So we need a function if we're going to be playing this game. And so, I don't know, why don't we use a parabola? Because we've done that quite a bit. Let's come up with a very simple one. How about y equals x squared? Okay? And so I can graph y equals x squared. So it goes through 0, 0. It goes through 1, 1. It goes through 2, 4. And then it takes off, right? So I have that idea. And here's a problem that I know you know how to do. Problem. Find the slope of the tangent line at 1, 1. Then I'm going to say, then find an equation of this line. So these are things that I think you know how to do. So I'm going to pause and let you do them, and then we'll go ahead and talk. Okay, so a lot of people know what to do here. We say f of x is x squared. So f prime of x is 2x. And we need to use that, right? If we want to find the tangent line, we use the derivative. And how do we use it? Well, we compute f prime of what?
1.
Why 1? Well, that's the x value of this point. And so you plug that in for x. And so you get 2 times 1, you get 2. And so what that means is, if I were to draw the tangent line here, just touching, it should have a slope of 2. That's the tangent line. Get with me?
So far, so good.
So far, so good. Okay. Oh, also find an equation of this line. Let me go over that also, just because these are the kinds of things you're going to have to do next Monday. So when we say find an equation, most people that I saw were using point-slope form. Right? That's useful if you know the slope and you know the point. And we do, right? We have everything we need, and so people wrote down, well, y minus 1 is 2 times x minus 1. And if you wrote that, yeah, that's correct. Some people went further and put it into slope-intercept form. Y minus 1 is 2x minus 2. So y equals 2x, I guess it would be minus 1. Some people like that better. But either way is fine. Okay, so there's my answers. So that's the tangent line. Guys with me? Okay. So here's the game. I need to explain what I mean by a differential. And I want to point out that the title of this section was the differential and linear approximations. We're going to approximate functions by lines. So if I go back to my picture, you see this curve and you see this line. Sometimes it's easier to compute what you want to know about a line instead of actually trying to compute the curve. Okay? Well, this is going to be a little fabricated because this example, x squared, is about it's easy to square something. You just multiply it by itself. But imagine that that's hard for us to do. Okay? Well, lines are easy. Lines are always easy. I don't care what the function is. A line is easy to understand. And so we're going to use the differential to help me kind of move along the line. Now, when I say delta x, remember what I said? I said dx equals delta x. In my example here, let's suppose we're going to move from the point 1, 1 to the point 2, 4. Right? What would delta x be in that case? Okay, so in my example, here's an example where delta x equals 1. You guys with me? What about delta y? Delta y would be 3. That's how much the y is changing. Well, so far, that should make sense to you. It's just change in x and change in y. And actually, what you used to do is find AROC. AROC was delta x over delta y. AROC was the slope of this line. Right? Okay. Well, now what I want to do is I want to talk about the differential. So dx is the same as delta x, right? So that's 1 in my example. But I said dy is not the same as delta y. Let me show you what dy is. This is dy. The differential dy would be, how much would the y change if instead of moving along the curve, you moved along the tangent line? You see how it's different? Now, let me show you how this works. We know that this is a true statement. Right? dy, who came up with this notation? Leibniz. And who came up with this notation? Newton. Okay? Oh yeah, please. Thank you. So Leibniz came up with the notation on the left, and Newton came up with the notation on the right. They mean exactly the same thing. It's the derivative. It's the function that gives me the slope of the tangent line. It's the thing you just used, right? Well, one of the reasons that Leibniz came up with this was he wanted to talk about differentials, which he called infinitesimal quantities, very small quantities. Very small change in x, very small change in y. And so what he would write down is he would write down the other equation I had on the slide, which was dy is f prime of x dx. And I guess you could see that if you look right here, right? This we said is dx, this is dy. If I asked you guys, hey, find the slope of the green line, dy over dx is the slope of the green line at x. Do you guys see that? Just like the slope of this black dotted line would be delta y over delta x. That slope is 3. So once you know that that slope is going to be this thing divided by that, you could actually compute what is dy. Well, it has to equal whatever f prime of x is times dx. So in my example, we already computed what f prime of x was. Do you remember what this was in my example? 2, right? Well, you're right. F prime of x was 2x. So what I really mean, I guess, is that f prime of 1 equals 2. You're right. We computed what dx is. What's dx? It's the same as delta x. So what is it? 1. And so what is dy? Well, I can compute it, and what do I get? 2 times 1 is 2 instead of 3. Okay? So the differential dy, is it close to 3? I don't know. I'm off by 1. Okay? I'm going to be off a little bit. But this is the picture that you want to have in mind as you work through these problems. Okay? I want to go ahead and do a few other samples with you that kind of talk us through it. The first one's right from the book. Problem 10. This is not hard. This is just kind of getting used to the notation. So here's a function. We have 7x cubed plus 3x squared minus 13. And it says, okay, let's compute the differential and write our answer in the correct form. All right, so that's easy enough. 7x cubed plus 3x squared minus 13. I'm supposed to go ahead and compute the derivative, right? F prime of x would be 21x squared. You guys okay with that? I brought the 3 down. I left the 7 where it was. What's the next piece going to be? And the next piece?
Good.
Yeah, that's it, right? Because the next piece is 0. So plus 0, I guess I could write, but that's it. So this is nothing new. I guess what's new is the way we're going to write the answer. If we want to write the answer as a differential, we say this is dy dx, right? Using the Leibniz notation. And so I'm going to write, what does dy equal? Well, it's 21x squared plus 6x dx. Dan, you have a question? Okay. So that's what we're going to write. What's in blue? Okay. It's just kind of a different way to write the answer, but also maybe it's a different way of thinking about the problem, okay? Because this dy, again, represents in a picture how high you move if you move along the tangent line some short distance. Okay? That's kind of the idea. We're going to do another one. Problem 45. So problem 45, actually, I should probably pause and let you read it. This is the function. You're going to need some room for this, I think. Yeah, if you guys have a books, open them up. So we're talking about the annual cost of covering employees' vision and dental insurance. All right, so here's an application of the differential. Part A, we're going to compute the differential. That's easy. Part B is going to be my application. Okay? So I'm going to talk you through that in a minute, but you could probably do Part A in no seconds flat, so I'll let you guys do that. Hey, while you guys are doing this, I'm going to go ahead and type it into the calculator while you guys are finishing up. It's going to be useful to have a calculator out. So I'm going to go y equals 1,000 plus 110 square root of x, close parentheses. And all they told me was x has to be greater than 0. Why'd they say that? Why'd they say x is greater than or equal to 0? What's that?
You always have to pay.
Well, I guess I have to know what x represents, right? So what if, go ahead. Dylan. You can't have a negative number of people, right? And actually, there's another reason. What would happen if you put a negative number into this function?
You get an imaginary number.
Then you get imaginary, right? We want to keep it real, so we're gonna say x greater than or equal to 0. Okay? So when I go ahead and do my window, x min, I guess I should start at 0. X max, did they say anything? They didn't. X is the number of employees. How many employees do you think we might have in a company?
How big's the company?
I don't know. It's DeCorn Company.
Duckhorn.
DeCorn.
Duckhorn. Maybe 30.
30. It's a small company, startup company. Okay.
You got tractors and stuff.
So we'll do that. We'll put a mark every 10 and see what happens. Now, what about y min and y max? Well, I'll tell you one thing. Notice what y equals. When you plug in 0, you already have $1,000, right? These are annual insurance costs in dollars. So those are like your fixed costs, right? So I guess I'll put 0, but we're working in thousands here. So why don't I put, I don't know, 5,000. And I'll put a mark every 1,000. And then we'll see what happens. If we need to change the picture, we will. Okay, so what's that? That's a graph of, well, the cost of my vision and dental insurance. And it looks like as x increases, what was x again? X is the number of employees. Then the cost increases because they paid for the vision and dental. That makes sense. Okay, so let's go and back to the work you guys were doing. You were computing a derivative, and so I saw a lot of people rewrite the function. 1,000 plus 110x to the 1/2 power. I saw some people use the product rule. You don't really need it. You could just ignore the 110 here, and it'll work. F prime of x, first of all, what's the derivative of 1,000? That's 0. If you use the product rule, you'll notice one of the pieces goes away. So what you get is you get 110, and then bing, 1/2, and then x to the negative 1/2, and then bong. Well, this time the derivative of what's inside is just you're taking the derivative of x, so it's times 1. So really what you get is you get, I guess, 55 x to the negative 1/2. Does that make sense to you guys? Now remember, for a differential, what you want to write is you want to write dy equals f prime of x dx. So I can do that. I can basically, instead of writing just dy dx, which is f prime of x, I can write it in this form. I can write dy is equal to 55x to the negative 1/2 dx. Okay? So there's dy is f prime of x dx.
You don't have to keep it in negative x prime.
I will. I mean, it doesn't matter. You could put the square root back in. You could write it as a fraction. We could check what the book did. I didn't check. I'm more interested in part B, but this is the answer to part A. Part B is where we're actually going to use this. So let's take a look at what it says exactly again. Okay. Suppose the company's CEO decides to hire 4 new employees. Question is, is that going to cost us? How much is that going to cost us? He knows what he's paying for salary. Okay? You like that picture there? So I have nothing to do with this. But the other thing is that the vision and dental, there's a cost associated to it. 4 more employees is going to bring up the rates a little bit. So the CEO says to HR, hey, how much more is 4 more employees going to cost me? Well, it depends. You can use a differential to get a quick answer. Okay, so that's what we're going to do here. And by the way, it says the number of employees increases from 250 to 254. Right?
So 6 differential or 4 differential.
So what is 4? That's a good question. You're right. 4 is the dx, because dx is delta x. That's right. So I want to sketch a picture of part B. Part B. And by the way, my graph that I had before on the calculator, this doesn't quite cut it. Not exactly. Why? Because Dan told me I had a small company, right? He said 0 to 30. Well, that's okay. But it's okay because I kind of know what it would look like. If I were to draw the curve, let's say right around x equals 250, going up to, say, 254, do you guys think it would be increasing or decreasing, this function? You think increasing? How come? Well, yeah. It's increasing from 0 to 30. You think it's going to keep increasing. If I want to know if a function is increasing or decreasing, one thing I can do is look at the derivative and see if the derivative is positive. If it's positive, then it's increasing. Look at our derivative. Some of you rewrote this as 55 divided by what? Square root of x. And there's something really cool about this function. Square roots are always positive. 55 is positive. So this function, the original function, is always positive. That means the derivative is always positive, so the original function is always increasing. So those of you that said it's increasing, I say, yeah, you're right. It looks something, the picture, if I zoomed in at the right window, would look something like that. It's increasing. You guys with me? Now, what I'm going to do here is I'm going to use the differential. I know that dx equals 4 because that's delta x. And now what I'm going to do is we compute dy. Okay? Well, using this equation. Okay? So I use this equation. 55 something to the negative 1/2 times 4. What do you think I'm going to put in for the something there? 250, that's right, because we're starting at 250, and what we're doing when we compute dy is we're moving along the tangent line. You guys see that? We know that dx is 4. This, if I move along the tangent line, that's dy. It's not delta y, that's dy. But that's what I'm going to use as my approximate increase in cost. And this is done all the time in the business world. Hey, how much more is it going to cost me? Let me compute it. Boom, done. 55. What do we have to throw in here? We said 250, right? You guys see where that comes from?
Mm-hmm.
Okay. So I just have to compute 55. So let me do that. 55 times, well, I need 250 to the, how about I say negative 0.5 for negative 1/2 times 4. You guys with me? Enter. So how much more is it going to cost? $13.91. It's not a whole lot, is it? Okay. And actually, then you could tell them, hey, how much is it really going to cost? Less than that. Do you see why from my picture? Because what it actually costs is a little less than the green line. We moved along the green line when we did the differential. You guys with me on this? And let me go ahead and show you how this worked. Here. What we can do, let's press window again and let's get a good view. Instead of going from 0 to 30, why don't we go from like 240 to 250? No, let's go 260. From 240 to 260 so that it'll look a lot like this. Ooh. Well, I'll go ahead and press enter. Graph. But that looks really straight. And part of that is because I have to know, here, let me press trace. See, at 250, they say I'm at 2739. That's what the cost is. So I'll tell you what, let me change my window a little more and just be up and down from 2739. Let's go from Y min, let's go from 2700 to 2800. And I'll just put a mark every 10. See what that looks like. Okay, there's my function. Even that looks really straight. Okay, but that's the increase, right? So if I trace, it tells me that when I compute 250, right, f of 250, they didn't ask for this, but they could have. F of 250, it says, is $2,739.25. That's how much my company pays for vision and dental annually. $2,700. Okay? If I hire 4 more people, what will I pay? Well, 27, it's another $14, right? So, not very much. 27.50 something, right? You guys with me? That's what it says. Actually, because it's on my graphing calculator, I could tell you exactly what we'll pay. I'll tell you exactly what we'll pay. I'll just put in second calculate a value 254. So what I know is the exact value is right here. 2753.11. Okay. So if I take that 2753.11 and if I subtract this 2739.25, let's see what the difference is. 1386. Okay? Do you know what when I subtracted what I just computed? 1386. That's right. Get 1386. That's delta y. Okay? So the actual difference is 1386, but my linear approximation was 1391. That's only a nickel off. And that's not bad. Brian, you had a question. Go ahead.
My question is, what's the whole point of having it like bothering with the differential when we can just compute the ag? the exact.
Because a lot of times you can't. Not as quickly. It really comes down to speed of computation. Okay? There are many times where, you have to understand something about the book. I'm giving you this function. All right? And I'm telling you that, I can put it in the calculator, I can look at the graph, and I can actually make my computations. Okay? But in real life, I may not have that. But what I may know is I can compute a differential very quickly. Okay? Whereas the actual function is more complicated. Okay? You're right. In this example, it was almost or maybe just as easy for me to come up with the exact value as it was for the approximation. But this approximation is done quite often. Okay? That's a problem with trying to explain this at this level. But I do want to say that this is a very common application. You know the value for this x value, and we're about to study marginal costs. This is what marginal costs do also. This kind of leads into the next lesson, actually, which I'm going to start right after our break. Speaking of break, you guys look ready. You guys ready for break? Let's take it. Maybe I should just re-emphasize. Here, if I were to draw delta x or delta y, delta x also equals 4. Okay? But delta y does not equal dy. Delta y would be this much. Right? It's smaller than dy here. You guys see that? And I guess delta y ended up being 1386 and dy was 1391. It's so close that who cares? Right? We're talking about a nickel difference. So that's where differentials are useful, or linear approximation is useful if the error is very small. Now, what keeps the error small? Small dx, right? The fact that we only increased 4 employees meant, well, it's not much difference between moving along the line or moving along the curve. What if you increased 400 employees? Better not use differentials anymore. Because if you increase 400 employees, right, that's going to be much different than moving along the curve. You guys understand? So we like linear approximations because they're easy to compute, but you have to keep dx and delta x small for them to be accurate. So that's an important idea to understand. Okay, so I'm going to do one more sample with you of a problem from the book that we can do with differentials, and then we're going to move on to the last stuff, the marginal stuff today. So problem 40 says, use linear approximation to compute the 4th root of 15. Now, again, we all have a calculator sitting in front of us. This is what Brian's question was. Why would I ever need that? All right, imagine you're on a deserted island, right? What are you going to do? Count coconuts? There's only 3 of them. But then you say, no, I'm going to redevelop mathematics so that my new civilization, we're not primitive anymore. And so while you're sitting around on the beach, nothing else to do, you say, remember we studied square roots and 4th roots. I'm going to compute the 4th root of 15. This is real practical, right, guys? Well, it's a good exercise for us, okay? First of all, what does that even mean, 4th root?
Square root twice.
Square root twice. That's one way of saying it. You're right. I mean, I guess I should really pause and ask you, can you compute the 4th root of any number? We'll let you guys talk to each other about that for a few minutes while I start to write some things out. I just heard somebody do this. They said, hey, let's do 15 caret 1/4. And that means 4th root, whatever it means. And they got that, okay? Now that is my exact answer. Well, not quite, right? It rounded after 10 decimal places or something. That's close enough, okay? So I'm going to say that the 4th root of 15, okay, the 4th root of 15 is, I just lost it, guys. Get my calculator back out. 1.968, if I round. That's about what it is. Okay? But, I don't know. What does that even mean? The 4th root. Can you give me a number that it's easy to explain what the 4th root is? 16? What's the 4th root of 16? 2. Do you guys understand that? See, when I try to explain that to somebody, here's how I explain it. The 4th root of 16 equals 2. Okay, that's a fact. Because, do you know what I would tell someone? Right, 2 to the 4th power. Yeah. See, when you say 4th root in a math class, the word root is synonymous with solution. And so really what you're doing is you are basically solving the equation x to the 4th equals 16. And we know that one answer is 2. That's really what it means. Solve x to the 4th equals 16. You guys with me? So back to our problem. When I said compute the 4th root of 15, really what I could have said is solve what equation? X to the 4th equals 15. Does that make sense to you guys? Matter of fact, on my calculator, if I take my answer and raise it to the 4th power, I do get 15. That makes sense to you guys, right? So that's what we mean by the 4th root. And so you might say, well, how do you compute the 4th root of 15 using linear approximation? Well, another way to say solve x to the 4th equals 15 is this. Solve x to the 4th minus 15 equals 0. Right? I don't want to do that, Rob. Ignore that comment. Good comment, but ignore it for now. Okay. Let's do this. Let's graph the following function. Because we need a function, and let's do x to the 1/4 power. And again, I may not know what that looks like offhand. So this is where the graphing calculator can help. Let's type in x caret, how about I put 0.25 for 1/4. You could type 1/4, but you have to have in parentheses. Okay. And for my window, well, I just need to pick some good x values that are going to be near things like 15, right? So why don't I go from 10 to 20? Okay? I'll put a mark every one. What about y min and y max? Well, why don't we go from 0 to 4? Because we know that f of 16 is going to be 2. I'll put a mark every one. Okay. So again, here's my function. Actually, maybe it would be worth it for me to make the window, the x min, start at 0 so that you can see a little more what the graph looks like. Does that make sense to you guys? Because what's the 4th root of 0? Yeah, we know f of 0 is 0. F of 1 is 1. But then f of 16 is 2. All right? So the picture is this. It goes through 0, 0. It goes through 1, 1. But then it's not until it gets to 16 that it actually makes it to 2. So it grows, but it's growing slowly. So that's a picture. And we know what we want. Okay? We actually want to figure this out. F of 15. That's what we don't know. Boy, the green and the black look almost alike. I notice. All right. So again, I'm going to zoom in on this picture here a little bit. Try to draw what's going on a little bit better. Let's see if I can do it. Here's the curve. Increasing. Here's the point, 16, 2. Here's the point, 15, we don't know. You guys with me? If I say I'm going to do linear approximation, that means I'm going to move along what? The tangent line. So the picture is we're going to move along this tangent line instead of along the curve. That's funny because this curve is so flat and you're only moving one, it's going to be pretty darn close. So let me ask you guys this. What does dx equal? Okay, some people would say -1 because you're going backwards. Does that make sense? It could be 1 or -1. What about dy? Well, dy is not delta y. What dy equals is f prime of x dx. Right? So that's what we have to compute. So let me compute it. F prime of x is 1/4 x to the -3/4. That's my bing bing. And if you did bong, you'd get a 1. Okay? Now what do you think I want to use? I want to use really f prime of, what do I want for my x? Well, 15 is what I want to approximate. I don't know f of 15 yet, I'm saying. But I do know f of 16. Even on Deserted Island, I know that's 2. And dx, I also know that that's going to be 1. Well, -1. So dy, according to my computation, oh, I got to get f prime of 16. Let me do that. F prime of 16 would be 1/4 times 16 to the -3/4 power. Okay? Use a calculator. I don't need to for this one, but I will for this. 1/4 times, open parentheses, 16, close parentheses, caret, open parentheses, -3/4, close parentheses. So all that I get 0.03125. Okay? So when I say what's dy, dy equals 0.03125, well, times -1, so -0.03125. That's dy. And so now, how do I get f of 15? Well, I would say that f of 15 is approximately f of 16 minus this dy. That's my linear approximation. So it's approximately 2 minus this, well, maybe plus, but 0.03125 is how much I want to subtract off. Let's see what I get. 2 minus 0.03125. I get 1.96875. What did I get for the fourth root before? I know I had it. It was really close to that, wasn't it?
1.968.
1.968. Yeah. Well, okay. So is it exactly the same? No, it's off a little bit, but it's not off until you get to the 1,000th place, right? Or 10,000th place. You guys see that? So this is a pretty good approximation. Okay. So it's approximately 1.96875. You could do that on a deserted island. You'd be just fine. Okay. All right, enough deserted islands. I heard the comment from the front row. It's too much math right here. Yeah, this is a lot of math, okay? But it's I want to show you examples that show you what the differential actually means. Again, it's movement along the tangent line instead of along the curve. Okay, so we're going to use these ideas now, and we're going to talk about marginal analysis, marginal functions. It's something that we hinted at last time.